Okay, good morning everyone, and thank you for participating to this first e-meeting of the Harmonious Cost Action. We organized this meeting in order to try to stimulate the collaboration that we already have and stimulate the activities that are ongoing within this working group 3. As indicated in the mail of our working group leader, Yijin Zheng, the aim of the activity, the aim of the meeting is to identify strategy to develop the guidelines for the estimate of soil moisture, soil water content using UAS. We have a wide range of activities that are ongoing that should be somehow channelized. The aim of the meeting is try to identify what has been done so far and what can be done in order to advance in this field. So please, Yijin, I'll give you the word and you can introduce the activities of the working group. Thank you.
Okay, thank you very much, Salvatore. And also our co-lead, Anna Brook, just joined. Thanks a lot for making your efforts here. So I will share my window with the PowerPoint. Can you see it now? Can everyone see my screen?
Yes.
Okay, nice. Then I will start. How to do? Okay. Okay. You can see it with a full screen, or it is just a slide. Hello?
Better to avoid full screen.
Yeah. But now you can see my, okay. It's very strange.
Or I suggest to change your,
Now it's
display
okay?
settings. Yeah, great.
Yeah, that's
okay.
perfect.
Okay, cool, nice. Thank you. So thanks all for joining this morning's, let's say, I would call it a kind of a brainstorm workshop in terms of defining the work task and also deliverable for work package 3, working group 3 soil moisture monitoring. I will go straight forward to the task to keep time on the track. So there are 4 tasks in this working group. The first one is about training school. The second one is about the spectral model for grade content, and then the third is intercomparison between different protocols and in the comparison of the measurement and ground measurement. Okay, this is of course a specific task, but then I mean basically for the working group 3, it started already 2018, and then back then Nunzio and Paolo supported the field work already since 2018 for working group 3. So there were already a lot of works has been done. So I will just go briefly, and then later on I will briefly introduce the agenda for this morning, and then we'll continue from there. So the first one about training school, actually this is just before the lockdown of this COVID situation in most of the European countries. We managed to have one a training school organized in Villach, and there we have 2 let's say lectures and practical or exercise linked to soil moisture monitoring using UAV. One is with Antonino, utilizing thermal inertia for soil moisture monitoring, and there is already one manuscript out of it. And Antonino also will introduce those essential steps for this later on. And then one is by me utilizing the random forest algorithm, and then downscale the Sentinel-1 soil moisture product at 1 kilometer to UAV pixel resolution, like 16 centimeter. The second one is about spectral-based model for assessing the clay content on the soil surface. For this task, basically Eyal and Nicolas Francos have done a lot of measurements in different fields, and there's also a manuscript just prepared for this task. The third one is about intercomparison among different survey protocols. So I understood from a working group 1, there's already a current practice in UAS-based environmental monitoring. I think this protocol, or let's say best practice, can be also utilized or applied for the working group 3 in terms of soil moisture. Good thing is Anna is there, Eyal is there, and also there are other working group 3 members are there, know the details. So later on, when we are preparing the guidelines for soil moisture monitoring using UAVs, this will be also referred to in terms of how we still need to figure out later on. The last task is about intercomparison, or let's say validation between UAV measurements and ground measurements. So again, this thanks a lot to Nincho and Paolo. This data collect from Alento were implemented already in 2, let's say, manuscript. One is just published in Water, based on the iAqueduct project. And the other one, as I mentioned, Antonino prepared already a manuscript in terms of thermal inertia for soil water content mapping based on 2018 campaign. So there are already a lot of works done, but those tasks are what I just mentioned that you can see from the let's say in terms of manuscript and publications, but there's a lot of field work support, logistics from behind. So again, thanks to Nuncio and Paolo, I want to highlight the importance of Harmonies and iAqueduct research bed. I mean, Alento subcatchment here. This is the location of the Alento catchment over there, and then currently there are many many in situ, let's say soil moisture, soil temperature probes, and there's wireless, let's say network there. So it is called SoilNet. And other than that, there's also cosmic ray probe. There are much more works has been done in terms of piezometers, but also sampling, a very intensive campaign to sample the soil samples over there in order to provide some further information for different type of researchers. So the main aim for this working group 3 soil moisture is to define a shared methodology to understand the spatial temporal pattern or behavior of soil moisture over different scales. And at the end, we have to deliver guidelines for soil water content monitoring. And for that purpose, I think it is good to have a brief catch-up this morning with the agenda presented here. So as we know, the soil moisture spatial temporal pattern is not only about soil moisture, right? It is all linked to atmospheric forcing some physical features, and those features are either dynamic or either like soil texture physical features. So that is why I think Monica can have a very nice contribution here to describe UAV from UAV perspective, how to measure the land surface energy, water, carbon fluxes, and what are those essential steps we can be identified also for soil moisture UAV monitoring, because anyhow the soil moisture is linked to those energy, water, and the carbon fluxes. And then Antonino later on will introduce the thermal inertia for the soil water content mapping. What are those essential steps we need to pay attention to? And then Nicolas later on will follow with the infiltration rate utilizing spectroscopy measurements. And then Brigitte following on will talk about machine learning, big data in terms of hydraulic pedal transfer research. And then Rodan is lately following up the random forest approach and plus UAS. And then at the end, we will see how far we go. Of course, I defined here 1.5 hours, but then let's see how it goes. Okay, is there any questions here? No, if not, then I will stop sharing, and let's go on with the agenda. Let me see. You don't see any screen now, right? Okay, cool. So now I think the next, let's start with Monica.
Okay.
Monica, do you know how to upload, present?
I've never used this one. I tried. Where are my slides? Sorry. I think I need to choose this. Do you see my screen?
Not yet.
How about now?
Yes. It's something.
Seems
yeah,
yes.
something's coming. Yes.
But I shouldn't share with full screen, right? You said.
I
just like that.
well,
No.
you can try. Yeah.
Or
you
do
can
you?
try.
No, then it goes to the other. I don't know because I have some animation.
Okay.
Which screen are you seeing?
Yeah.
Okay, I try like this.
Okay.
So thank you very much for inviting me. And I'm sorry I have to leave at 11:15. I couldn't postpone the meeting I have afterwards. And I think the discussion is really, really interesting. But
yeah.
At least I try. So
well, thank you very much for making the effort. So that's why I moved you to the first.
I saw. Yeah, I postponed 15 minutes more, but
yeah.
But anyway, so the idea is how to all these fluxes, the water, the carbon, and the land surface energy are connected, and then remote sensing can help us to model them. And maybe not working. I don't need to. Sorry, the animation don't work. You just see my screen.
Yeah.
This is not gonna work. One moment. Sorry, I want to change the screen that I'm sharing. This one. Okay, now you know I'm all using Microsoft Teams, Google, not this one, Zoom, Skype, but not okay. So, okay, do you see the screen with animation now?
Yes.
So anyway, this is a very basic, so maybe I can go fast. But the point is that all these ecosystem functions, the exchange of water, carbon, energy between the land surface and the atmosphere are interconnected. So a change, let's say, in vegetation cover will affect how much radiation is absorbed, will affect the albedo, will affect the energy balance, the amount of energy absorbed for photosynthesis, the evapotranspiration, and eventually also the runoff. So if we want to understand what happens in one of these cycles, we need to understand what happened in the other cycle and also exploit this information together. And actually nowadays, a lot of the uncertainty in the hydrological cycle comes from the uncertainty in the exchange of CO2 and water vapor between the plant canopy and the atmosphere. So the stomatal conductance is really causing a lot of uncertainty in these estimates, for example, responses to climate and what is the effect on the hydrological cycle. Some of the things we are working in the context of Harmonious is a project called Agricultural Water Innovations in the Tropics with Hong Xiaojin, the postdoc.
Monica, sorry.
Yeah.
Monica, sorry. I think when you turn your head, and then the audio is not very clear.
Oh,
Yeah.
I see. Yeah, I have the screen really fast. So in this project, we are using UAVs to try to assess the effect of different instruments like biochar to reduce the water footprint of crops in tropical dry regions like Costa Rica or Brazil. And we are working in commercial farms with ecovariant systems and also in some experiments where we are testing biochars. So, and one thing is, soil moisture. So, and we are very interested in this collaboration. So the idea is that some of the traits that we can sense with remote sensing, like pigments or water content in the canopy, are really well known and established. In the thermal, we tend to use broadband information. If we could use hyperthermal, I'm sure we could see a lot more things. And some of you, I think the Israeli group has also this kind of sensor. But how can we go from this, like, let's say, morphological traits and plant canopy attributes to function? So the idea is that we can see some changes in plant functional gradients, and then we can use radiative transfer modeling, and there is some link between the two. But the mechanistic links between reflectance and emission are not really always clear with, let's say, photosynthetic efficiency or stomatal conductance. Is much more indirect. Also, many times we try to scale up tissue level traits like leaf water potential to individual canopy and large pixels, how to do that. Also, not all relevant traits we need, let's say, for models have thermal responses or optical responses, so we have to find proxies. Also, another aspect, I think with remote sensing, we focus a lot on static or snapshot modeling, but what we do when we don't have images or observations, and what happens also in transient conditions. And another thing is like, because how plants adapt to the environment, it has been observed that the same set of traits, of plant traits, can lead to the same function, to the same, for example, transpiration. So it's like a bit like equifinality, but in nature. So this is what we are dealing now, and what I have been working with is using the as a link for between remote sensing and function, use the energy balance. The first law of thermodynamics, the net radiation can be dissipated as sensible heat, latent heat, or ground heat flux. And some of the components of the shortwave depend on the trace that we can sense, like albedo, pigments. We have also the surface temperature and emissivity that we can use remote sensing. Then we have the latent heat flux that is driven by vapor gradients and modulated by the resistance to that transport, the aerodynamic one that depends on trace like canopy height, how rough is the canopy, how well coupled can it be to the atmosphere, and the surface resistance, or the stomata related with the stomatal conductance that we can maybe estimate indirectly by changes in how when it closes, the temperature of the leaves will increase, so we can observe some changes in this conductance. And then we have the sensible heat flux that is driven by the temperature difference between the surface and the air. So from remote sensing, we can have the surface temperature. And again, we have an aerodynamic resistance that indicates how well coupled is the surface that we are measuring to the atmosphere. And the ground heat flux, and also photosynthesis is part of this, although typically it's so small that we don't use it, but a small fraction of the energy comes into photosynthesis. And here I want to highlight some of the struggles we have when we apply remote sensing models to solve, for example, latent heat flux, sensible heat fluxes, the resistances, how to implement them in space, the aerodynamic one that depends on the roughness of the surface and the stomatal resistance. And another aspect is that the temperature, I think Antonino will explain a lot more about this, maybe that what we sense, the radiometric temperature from the sensors, is not the same as the aerodynamic temperature. And finally, we can also consider use the first law of thermodynamics, but in a dynamic way, and consider that most of these components are affected by the surface temperature and also modify it. So this can be like our linking variable between this structure, function, and energy balance. So what we do is in our lab, we work now, we have different payloads with drones, imaging spectroscopy, a cover camera in the visible and near infrared. I am highlighting the ones we are presenting today, thermal and then a navigation payload. And a lot of our effort goes here in the corrections before we can get okay data. And so far we are implementing radiometric, geometric, atmospheric, and we are trying an isotropic BRDF corrections, but we are not there yet. Here is an image of what happens in Denmark with clouds passing. We have a lot of problems with clouds, but also in the tropics we have seen the same. It's very hard that you have a clear day with no clouds, so I think that's an aspect that harmonious maybe we can discuss. And then assimilation into different kinds of models and evaluation in covariance flux size, typically of the model output. And the approaches that we can use for estimating function like carbon, water, and energy fluxes, typically we connect an energy modeling, a radiative transfer model, and a flux model. And we can have top-down scaling models that use simple rules like big leaf for estimating the fluxes, and simple radiative transfer law like Beer-Lambert and broadband approaches. We can have more mechanistic bottom-up scaling models where the energy is solved with using more detailed radiative transfer model like Rossell, Dart, and this can be coupled at the leaf level with the fluxes, like that's what, for example, a scope model from Christian van der Poel does. And we can have also data-driven models where you just link statistical models with the parameters we want to estimate. For example, they have been able to estimate maximum velocity of carboxylation of leaves using hyperspectral sensing in Brazil. So we can use these data-driven models also to explore relations where we don't know exactly the mechanistic relation between the function we want to model, like photosynthesis, and what we detect with remote sensing. And one thing we have been doing in DTU is develop a crop monitoring system over flag sites where we estimate with a top-down approach, a conceptual approach, CO2 water consumption, and also try to estimate in between flights what are the fluxes. This has been done in 2 flag sites we have, and also continuing in Costa Rica. One is in a willow plantation here on the right in Denmark, another is a beech forest. And the first thing we need, or a key variable we need to model evapotranspiration, or in this function is the root, what is the root zone soil moisture. We have a complete vegetation cover, so methods like thermal inertia might not work so well. We were thinking that from the drones we can get 3 height proxies based on the structure from motion. We could also get this from LiDAR, and that's more costly. But this should have an influence on the soil moisture because of the roughness of the canopies is going to affect how they exchange heat with the atmosphere. The degree of coupling is going to be different depending on tree height, and that should be reflected in the top of the canopy signals of temperature. And we also wanted to see what was the soil moisture that we model is detecting soil moisture in the upper layer, in the root zone, and what is the area of influence of the soil moisture that we have now very high resolution, so that opens up the possibility to see what is the optimum resolution to detect this. So we have not as good setup as in Alento, but we have portable TDR in some dates and also some in situ sensors. This is the willow forest, and we just use height, NDVI, surface temperature, and in different dates in this forest. And many of you know this triangle approach where you plot the fractional cover with surface temperature difference. So these pixels that are along this edge should be dry pixels, and those with no temperature difference between the surface and the atmosphere should be wet pixels. But with the drone, the problem is typically we don't have all the hydrological conditions, so we have to model what is the dry bare soil. And another thing is that we assume that these pixels all have the same, the only source of variation in temperature is soil moisture. So changes along these vertical lines are related to changes in sensible heat flux, because it depends on the temperature gradient. And then we are somewhat implicitly assuming that the aerodynamic resistance, which is in the denominator of the sensible heat flux, is not changing. But we thought, what if we correct this axis with the aerodynamic resistance that can be estimated based on the tree height? So here is a bit more conceptual, this triangle. We have the dry edge, the wet edge, and any pixel in this space can be rescaled between these 2 axes, and gives us a proxy of what is the non-evaporative fraction, the ratio between sensible heat and available energy. And then from there, we have a proxy for sensible heat, or an index between 0 and 1. So, and we can embed with a very simple model to estimate soil moisture. But we also need to know what is the minimum soil moisture and maximum, these 2 thresholds, where the soil moisture decreases more or less the evaporative fraction, or the non-evaporative fraction, in this case, decrease linearly with soil moisture. So we apply these concepts in different dates, as I say, with correction for tree height and without correction for tree height. And the results were improved when we use the tree height correction. Also, we observed that the correlations were better with the root zone soil moisture, and also with diameters of 50-30 centimeters that were related to tree crowns. So the problem that we found, that I bring it here for maybe discussion, is we found that in a way we have sense the temperature of the canopies very well, very high resolution, but the models that we have to estimate aerodynamic resistance, they kind of wipe out this signature, because they assume that the blending height that happens, all the it needs like a mixing length. So the models that we can apply cannot take advantage of this high spatial resolution, but this high spatial resolution has been shown that matters. So how can we reconcile these two things? Maybe something of interest for discussion in harmonious. Because nowadays we don't have these tools. Sorry, I didn't check the time. How with time?
Yes, you have 1 minute, but please go ahead.
Okay. Now, then this next is the evapotranspiration. This is just presentation of the model we are using. The evapotranspiration has been applied for satellite data. We use a thermal inertia because in dry regions where I work a lot, didn't work so well, the approach that they have, but a very simple thermal inertia approach. And how we connect the evapotranspiration with the gross primary productivity is because we assume that the constraints that reduce transpiration from potential level can be like multipliers related with environmental factors like temperature, green fraction, soil moisture, are the same, affecting the fixing of carbon, because the somatal conductance is the same. So this model is simple, but it's good to introduce in any of these constraints different types of remote sensing data sets. So we try to put these constraints used for canopy transpiration into the gross primary productivity, and we assess with drones the effect of what is the optimum resolution to estimate these fluxes using eddy covariance, and also perform some validations, which I won't go into them. But we use the footprint of the eddy covariance and the footprint in different parts of the day, samples different parts of the field. And this tells us that the spatial pattern that we detect matter, because if we average this spatial resolution, we see that the estimate is not as good, because of the sensing by the eddy covariance system is not the same for all the pixels in the footprint. There is a weighting factor. And finally, this is about the dynamic modeling, what to do when in between days. So we use this top-down evapotranspiration and carbon model, and to use it between dates, we just use the transient equation for changing surface temperature using the force restore method, and a simple bucket model for water, for soil moisture estimate. And then we just use the drone images to calibrate some of the parameters of this model. So we take those images as ground truth, like the soil moisture and the surface temperature, and then we calibrate some soil parameters and plant parameters that we needed to run the model, and then we just run the model with climatic forcing in the whole system and NDVI. So, but NDVI changes less rapidly than, let's say, surface temperature, so we can use interpolation, linear interpolation and time series for that. So these are some of the results for modeling surface temperature in between observations, net radiation, soil moisture. So I'm going to skip this because this is using machine learning to predict the stomatal conduction, transpiration, and photosynthesis. And my summary is that this exchange of water energy and carbon are interrelated, and we can use the energy balance as a framework to assess different parts of this energy balance. And all kind of models have their own merits. We saw that crop height improves soil moisture, estimates in the root zone, and also that we can use a top-down scaling model to estimate gross primary productivity and evapotranspiration and perform gap filling using a dynamic model. And also, I didn't present, but using hyperspectral data and thermal data in a machine learning partial linear square regression, we can predict leaf physiology for crops like soybean and maize, which present different regulation of stomatal control. So, this is my presentation. Thank you.
Thank you very much, Monica. It's very interesting.
Sorry about the rush.
No.
Thank you.
Are there any questions?
Shall I stop sharing?
Maybe I have one, and then maybe we continue with Antonino. Monica, so I saw it's very interesting, especially you trying to utilizing the tree height and to get a better root zone soil moisture. So I saw you, let's say, after the correction, then you get a better result. So you applied also over the different, let's say, canopy height, right? Over short grass, over tree, over. No.
No, that's the thing that our site, in that sense, was a bit. Is this willow? Maybe I have. It's a willow forest, very small here. Let me try to see the picture. It's a willow forest, and it's very homogeneous.
Okay.
So it has some variations, but we really wanted to test it in a site or different sites that have different tree heights. The thing is, it in a space was very homogeneous, but over time it changed quite a bit. So to not break the rules of this, estimating aerodynamic resistance and so on, Monino Bukov, we could apply different tree height over time. To apply different tree height over space at the spatial resolution of 40 centimeters, we will break some of the conceptual assumptions. So we develop something related that we take into account the boundary layer conductance, but I will say our data set was not good enough to test that. And then we also face the problem that the models to estimate the resistance are not prepared to address very, very high spatial resolution. Maybe then we should use like computational fluid dynamics or something.
Okay.
So, and that's a bit I think where something could be very nice to do more research.
Yeah, indeed. So like the 3D canopy structure, as you mentioned. Yeah, indeed.
Yes.
Okay, thanks a lot. For the sake of time, we continue with Antonino.
Hello, good morning to everyone.
Hi.
So, present my entire screen.
Just before you start, for Monica, can you share a presentation later on? Okay, thanks.
Okay, can you see my screen?
Yes. Yes.
Hello?
It's very
Okay.
nice to share.
Okay, thank you. So, good morning to everyone. My speech today is about thermal inertia, and I will try to outline the essential step in order to apply this technique on very high resolution images by taking as a case study the experimental site of working group 3. The outlines of my presentation. First, I will introduce the models that can be used in remote sensing for soil moisture estimation, and we will concentrate on thermal inertia with we'll define which is the aim of this specific application at vary from US data. We will give some theoretical background, and then we will try to take advantages of very high spatial resolution in order to extend the thermal inertia method to a whole domain, to the whole image. We will give some characteristics the study area need to have in order to apply this method, and then we will introduce that materials are required for this application, both in terms of remote sensing data and in situ data. We will discuss some results and then give a take-home message and outlining and highlighting also the limits of this methodology. So by introducing, there are several methods that can be applied in order to estimate soil moisture from remote sensing data. Some employs microwave data, both active and passive, and these are not suitable due to the weight of the sensor in order to be applied on US data, in my opinion. Recently, thermal inertia and triangle method data, Monica just before introduced, are two techniques that are quite widespread for as techniques employing the thermal part of the spectrum and the shortwave part of the spectrum. Soil moisture is specifically used to determine the triangle method is specifically used to determine the soil moisture in the root zone part of the soil, because is linked to the evapotranspiration or latent heat flux and sensible heat fluxes processes. While thermal inertia is more suitable for bare soil due to the underlying hypothesis on the one-dimensional thermal transfer equation. Recently, thermal sensors become quite small and miniaturized in order to equip drones, UAS systems. Thus, we are looking within these activities if we can take advantages of the very high spatial resolution nowadays reachable from US, in order to select thousands of pixels where the hypotheses underlying the thermal inertia are fully fulfilled. If so, we can think to apply some geostatistical analysis in order to estimate spatial distribution of the thermal inertia that the thermal inertia would have over bare soil in the whole domain. So the theoretical background, the thermal inertia equation is the one in the top left side of the slide. Comes from the one-dimensional thermal diffusion equation and relate the forcing of the system, that is the irradiance in the shortwave part of the spectrum reaching the soil and entering the soil through the coalbedo, and the variation of temperature that of the surface part of the soil that is a consequence of the thermal properties of the soil through the thermal inertia. And the thermal properties of the soil depends on the characteristics of the soil, but mainly on the soil moisture content of the soil. Thus, the forcing of the system, that is the radiance and the variation of the temperature that follows these forcings, are out of phase of the phase difference, that is this term delta here. Also, this term B is a function of the phase difference, and the phase difference is a function of the thermal inertia itself. So this equation is quite difficult to solve. We can have some more hypothesis in order to obtain a number that is called the Kirsten number. It is a normalization of the apparent thermal inertia between the minimum value and the maximum value it can assume. And these hypotheses are a small extension of the study area in order to take as a constant these terms A1, clear sky during the whole day, in order to have a sinusoidal behavior of the irradiance reaching the soil, bare soil, in order to have a variation of temperature of the soil that is consequence only to the irradiance reaching the soil and not to evaporation of sensible heat flux or latent heat flux can occur over vegetated soil. Not shadow, not shadowed pixel, because in this case the behavior is not sinusoidal but is like with the exponential decay, and assume that the phase difference could be is constant spatially in order to normalize the value of the thermal inertia in a very straight way. In this case, we can assume that the Kirsten number, the normalization of the apparent thermal inertia, could be assumed almost equal to the normalization of the apparent thermal inertia. That is this term called albedo divided difference of temperature. Once you obtain the apparent thermal inertia, you can use the Murray and Birov equation that actually is based on the Johansen approach in order to relate the Kirsten number of the apparent thermal inertia on the soil with the soil moisture. And under a small range of variability, you can try to use also linear approximation of the Murray and Birov equation. And to do this, you need to calibrate the equation over suitable pixels that are those that are not vegetated and not shadowed during the whole day. Okay, so we are using 100,000 of bare soil pixel and not shadowed as ground truth in order to obtain the apparent thermal inertia on pixels that fulfill the hypothesis underlying the thermal inertia theory. Okay, so we can then spatialize the apparent thermal inertia in order to obtain an apparent thermal inertia that would characterize our domain in due to only soil moisture. So we are not taking into account the presence of the vegetation or shadows that would change the value of difference of temperature between during the day. In order to do this, we can calculate a theoretical semivariogram of the apparent thermal inertia and then to be fitted to an empirical semivariogram evaluated on these thousands of pixels. Once this is done, you can spatialize the apparent thermal inertia and convert the apparent thermal inertia in soil moisture, applying the previously calibrated equation. Because this soil moisture will be on the wall domain, you need to validate your data, taking into account the wall dataset, the points acquired on bare soil, but also data acquired on bare soil, but also data acquired on vegetated soil or in shadow. About the study area, we are using the data acquiring during the first campaign in October close to Monteforte Cilento village in the Alento River Basin. Was a small catchment. What is important to say is that you need peaks that are not vegetated and not shadowed by at least at the resolution of the thermal images. And the area has to be quite small in order to avoid taking into account the variation of thermal inertia due to latitude. So other materials you need to collect in situ: spectroradiometric data for sure in order to calibrate the multispectral images, GNSS data, RTK acquisition is a fast method in order to have a good orthorectification of your optical and thermal images, for example, using a structure from motion approach. The soil thermal properties in order to have to characterize which are the extremes of the thermal inertia for this kind of soil, for this type of pedology with full variation of soil moisture. And some thermal images acquired with an handheld thermal camera in order to calibrate the thermal orthophotos, and soil moisture data acquired both over those suitable pixel, but also over pixel vegetated on under shadow, in order first to calibrate and then you validate your methodology. You need to acquire also images, thermal images, for example, are suitable to be acquired at sunrise when we have the minimum of daily temperature, and a couple of hours after afternoon when the soil reaches the maximum temperature. Simultaneous to this second acquisition, you need also an image in the shortwave part of the spectrum in order to calculate the albedo, the shortwave albedo, and then the coalbedo. These second images for sensor due to sensor characteristics would have a spatial resolution that is higher than the one of the thermal images. So this second acquisition, the shortwave one, should be resampled at the resolution of the thermal images. And in my opinion, a good technique is of resampling. A resampling method is the pixel aggregation that simply average the radiance and then the reflectance of characterizing our high resolution pixels. So second step is to extract from our images through a Boolean mask pixels that are suitable to be used for thermal inertia calculation. And a good option, there are several methods to have a Boolean masking. For sure, random forest works quite well, and this is simple to apply. So once obtained sparse points of apparent thermal inertia, we are at this point ready to perform a geostatistical analysis in order to changes in space with lag distance. And my suggestion is to calculate also the anisotropy of the variogram, of the semi-variogram, because soil moisture exhibits some anisotropy usually in the field, and thus the apparent thermal inertia due to only soil moisture would exhibit an anisotropy as well. So once you have the semi-variogram, you are able to spatialize using, for example, a Kriging algorithm. Okay. On the other hand, you need to convert, you need to calibrate the apparent thermal inertia into soil moisture. So the Murray-Envirov approach, that is this continuous black line, is an equation that was calibrated over a wide range of soil texture, and is usually applied worldwide, but over a narrow range of variability, you can also think to use a linear approach in order to have an operational method. And in our opinion, a relative error of about 5% between the Murray-Envirov and the linear the simplification, that is the linear approach, is enough, also considering the splitting of the points on the regression lines. And thus you can convert the apparent thermal inertia in soil moisture, and you have a spatial distribution of the soil moisture that you need to validate. Due to the theoretical background, we expect that the regression coefficient between apparent thermal inertia and soil moisture is going to decrease. And actually in our case study, it decreased about 0.1. So from a determination coefficient of 0.7 for the suitable sparse points to 0.6 if validated over the whole dataset of soil moisture. So the determination of coefficient decreased, but the relationship remains quite good. So concluding, we are trying to extend the thermal inertia method on from not shaded, not vegetated pixels, also over vegetated and shaded pixel, by taking into account the very high spatial resolution offered by UAS acquisition. Unfortunately, indeed, thermal inertia cannot be applied also over vegetated pixels. And in this case, the determination coefficient was quite low. The determination coefficient increases if you take into account only bare soil or not shaded and not shaded pixels. In some case, over a narrow range of variability, you can think also to apply the linear model that is more operational compared to the Murray-Envirov approach, in order to convert the spatial distribution of the apparent thermal inertia into soil moisture. And the spatial distribution should be obtained in our opinion, using a semi-variogram analysis in order to take into account also anisotropy effect. After this processing, the correlation remains quite good, even though it is quite a bit smaller than the correlation over suitable pixels. And this is my last slide. So I thank you all of you for attending, and this work has been submitted for publication on transaction on geoscience and remote sensing.
Thank you very much, Antonino. Are there any questions?
Maybe just one question. Antonino, thank you for somehow the detailed description of the activity. Do you think it is possible to identify somehow standard procedures for this kind of application? Because one of the criticalities, one of the main limitations is the fact that several times we have to customize this procedure, and what can be generalized? What can we learn from these experiences? This is a more general question. It can apply also to Monica, really.
Okay. In my opinion, this kind of methodology has to be applied to small area in order to have a detailed description of the variation of soil moisture. For this reason, I would prefer to use a linear approach. Okay, and the linear approach is field-based because it depends on several factors, and the relationship between the soil moisture and the normalization of apparent thermal inertia is not a universal relationship. So I would suggest in each case to use remote sensing data to have a spatial distribution of a proxy of soil moisture that is the apparent thermal inertia, but then in each case to use some field data in order to calibrate the relationship. This is my feeling about this kind of application. The novelty with the previous research is that you can use very high resolution spatial resolution data in order to obtain in our case were 100,000 pixels, where you can assume that the hypothesis of the thermal inertia are fulfilled. And there are several hypotheses that allow you to calculate the thermal inertia starting from the monodimensional thermal transfer equation.
I also would like to ask one thing. Did you finish?
Yes.
Antonio? It is connected to what you were talking about now, that you mentioned that it is difficult to have a universal equation to find the relationship between the soil moisture and the thermal inertia. And do you think it would be possible to measure another information which could help to define a more universal equation. So if you have case studies in different sites, different days, and to find out what kind of other information you would need, which could help to get more universal equation? Is there, do you see any possibility for it?
Okay. About thermal inertia, one option is to have a third measurement of temperature. So in this case, we used two thermographies, one at sunrise and one a couple of hours afternoon. Also the multispectral images, but this is less important. If you use a third thermography, you can avoid some hypotheses in the calculation of the thermal inertia. To say the truth, you can relate the phase difference, that is the function of thermal inertia, with the soil moisture. So you can have a sort of a shortcut of several hypotheses underlying the method and find a direct relationship with the soil moisture. Unfortunately, both the Murray and Virov equation and the linear approach that we used need to be set up, customized for that kind of soil. The Murray and Virov equation depends on the texture of the soil, for instance. The linear approximation as well, but is valid just for a narrow range of variability. So one option would be to use three thermographies, but in each case, in my opinion, at least in my opinion, an empirical calibration to obtain soil moisture remains.
Okay,
Thank you.
thanks a lot.
I have a very quick question for both speakers. So thank you very much, Monica and Antonino. I have a general question. It seems, or maybe like, I think it should be highlighted, that UAS for a moment is a platform with a higher resolution than any other satellite or airborne system or sensor. It seems that for now, or correct me if I'm wrong, but for now, no other advantages than higher resolution, which can be also a problem for both speakers. You identified that some phenomena, they are really spatially related, and sometimes the UAS is too much, it's a higher resolution. And as Antonino mentioned, the aggregation to the pixel component aggregating, I understand what should be done. So I think maybe these studies should be more emphasizing the advantages of UAS, beside the fact that it's more easy to operate or collect data like that. I think that we miss here a very essential part of claiming why UAS should be in these studies. Again, besides the fact that it's very easy to collect, anyone can buy a drone and fly with it, but something more linked to physical property.
Yes. Yeah, I think you really hit one of the key things, like why are we using drones and they are not just small satellites and we just use them like that to get higher, do you hear me?
Yes.
Higher spatial resolution. So I think the higher spatial resolution is one thing, but also that we can fly below clouds, and then there is a lot of things happening differently when we look at things with diffuse radiation.
And shadowing and all this stuff, like beside the physical barrier, I'm saying like something that we can catch more unique.
Yeah, and what I think is so far, for example, I've been doing a lot of, or we have been doing a lot of transferring of satellite methods into drone methods. But I think
it's common. I mean, the comment is it's common that many of us started with satellites, and now we are like forcing a bit the same applications, the same strategies, the same hypothesis on drone data, and sometimes maybe it's not even correct.
Exactly, we should find their own niche. And for example, one thing is like, for example, what I show with the 3D canopies, we can sense like the high fine spectra thermal signature of canopies, well, both in the optical and in the thermal, but the methods that we have are not matching this, are not living up to that high resolution. We cannot apply them because, yeah, they are not conceived for that special resolution, and we wipe out this, we dismiss this in some of the methods. So I think how I have been thinking is drones, maybe a very interesting approach for me is to use them to take videos like very, very high speed, like turbulence, and then like, you know, ecovariant systems, but for, you know, from the air you can take the temperature variations really fast, and then maybe you know, we get a different layer of information.
Yeah, this is a good direction. I mean, you're justifying why to use this platform, and you're saying that you can send something absolutely unique and new.
Yeah. And I was also thinking with Antonino, do you think you can look at soil moisture really at the surface and what the plants are doing and what happens below might be decoupled? Do you think could be interesting to link what you see at the soil surface and then from the plant canopies temperature, what looks more below ground, and try to sense what is this coupling?
Nice question, Monica, because this is one point of this method that is often misunderstood from several colleagues. It's true that with thermography we are looking at the skin temperature. Okay, this is true. But the skin temperature is a property that depends on the thermal properties of the soil. And the thermal properties of the soil are the thermal conductivity, the thermal capacity, okay, and the density of the soil. These three parameters depend on soil moisture, and that's why the thermal inertia is dependent on soil moisture. It's through the thermal capacity, through the thermal conductivity, and through the density of the soil.
Antonino, but there is
but there is a crust.
Yeah, no,
right?
but there's let's say certain footprint, right?
Yes. And the first part of the soil, and it's called is a quantification, is called the damping depth, influences the surface temperature. This damping depth, for instance, in the case of Monteforte Silento, was about 15-30 centimeters, depending on soil humidity. Okay, so with thermal inertia, you are estimating using a surface temperature, a skin temperature, the effect of the soil moisture in the damping depth on the soil moisture. Of course, the surface layer of the soil is more important than the deeper layer of the soil. And the weight is decaying exponentially. While, for instance, in the triangle method you shown before in your application, the temperature behavior in the temperature vegetation index feature space is a function of latent and sensible heat flux. So in that case, it is dependent on the soil moisture available to the root zone. So we are talking about different part of the soil and also the change depth depending on the soil moisture itself, in the case of thermal inertia, and on the root zone distribution within the soil in the case of the triangle method.
Oh,
I don't know if I answered to your question.
okay, thanks a lot, Antonino. I think this discussion is very interesting, and we should take it into account later on afterwards discussions. So now, consider of time, let's move on with Nicolas. Hi, Nuncio.
Hi, Jan. Thank you.
Hi, Nuncio.
So I'm going to.
Yeah.
I have to see here how to show the presentation.
Hi, Nuncio.
Do you see?
Not yet. Okay.
It's coming. Here it is.
Excellent. So today I'm going to talk about a paper that I submitted last Saturday. It consists about the campaign that we performed last year in Alento, and then I worked in this data and the results. So estimation of the water infiltration rate of soil using reflectance data from ground and the UAV platforms. So soil spectral libraries are datasets that contain chemical and physical soil properties as well as laboratory spectral measurements. And the number of these datasets are increasing because these datasets have an important potential to be used as training datasets to monitor soil properties from the sky. Once these datasets are adapted to the configuration of the airborne or satellite sensors. The problem is that because soil spectral libraries are created under laboratory conditions, it is not clear if they can be used to infer field conditions, because once we collect the samples to the laboratory, the samples are, the soil crust is starved. So to study this gap, we chose the water infiltration rate because this is a soil surface dependent property. This property can be defined as the length units per unit time of water entering to the soil, regardless of the type or values of, or forces or gradients. So that means that once a drop of water disappears from the soil surface, it means that it is considered as water that infiltrated. In the literature, I found several papers that reported relation between water infiltration rate and the other soil properties, between them the energy drop of water. Agassi at 85, he found that the energy drops are negatively correlated with the water infiltration rate, because once the drops falls to the soil surface, it the soil particles jumps up, and then those particles that weight more falls before, and then those particles that weight less remains up, and this phenomenon decreases the infiltration. Then at 94, he found that this effect is cumulative. At 2004, Lado found a positive relation between water infiltration rate and the organic matter, but Capriel at 97 found that a specific kind of organic matter, aliphatic bonds that are rings of hydrogen that surrounds carbon, had a negative correlation with water infiltration rate. So not all the kinds of the organic matter affects positively the water infiltration rate. Benur and Litey found negative relation with water infiltration rate. Stern found the same with smectite, which is a clay mineral, but in the same paper he reported that illite and kaolinite, that are also clay minerals, foments infiltration. So not all the clay minerals have the same relation with the water infiltration rate. This is the apparatus that I used to measure the water infiltration rate. This is the mini disc infiltrometer. And this is an apparatus that we connected to an ASD spectrometer to measure the soil surface reflectance under optimal conditions. So we acquired the laboratory field and water infiltration rate measurements in 6 different fields, and in total we collected 114 samples to build this dataset. Here you can see how we take spectral measurements in field with this apparatus connected to an ASD spectrometer. So the advantage of this apparatus is that using this device, we can neutralize the atmospheric attenuation, and we can get spectral measurements in field with almost a laboratory quality. Here you can see the information that we can lose once we collect the samples to the laboratory. Here in this picture, you can see the undisturbed soil crust, and here the disturbed soil crust. So indeed there is a gap that is necessary to study, and here we can see the spectral response and the ratio between them. So when we see the ratio, when the values are farther or lower than 1, it indicates that these spectral features are more loose when we disturb the soil surface. Between these soil spectral properties, we can highlight the slope of organic matter in the visible and the near infrared spectral range, some spectral features of iron oxides, hygroscopic water, and clay minerals. Here you can see the fields from where we collected the samples. Between them, Kibbutz de Yoav in the south of Israel, in Afeka in Tel Aviv, in Alento in Italy, and also we were in 3 different fields in Greece. This texture triangle shows the average soil texture of every field. So it was possible to classify the data into clay and sandy soils, and also I created a group using all the datasets. We can see that the dataset has a varied texture, and to predict the texture of the samples, I used spectral-based models. The texture of the samples is very important to calculate the water infiltration rate, because with this information, we use specific coefficients that are necessary for the calculation. So, experiment design. We performed spectral-based models using the not resampled and then the resampled data set according to the spectral configuration of the cuvert, which was the sensor that we used to scan the Alento study site with a drone platform. The best spectral-based model that was then applied to the UAV hyperspectral cube. From this image, we selected the pixels that were considered as a bare soil, and then by using the IDW interpolation method in the measured water infiltration rate and then in the predicted infiltration rate, was possible to compare especially the maps to generate the prediction map. We selected randomly 100 pixels in order to get a smoother interpolation, and that is in general. You'll see the results. So when I use the world dataset, here in the left, you can see the spectral-based models that were generated using the ASD spectral resolution, and in the right, once the spectral data was resampled to the spectral configuration of cuvert. So in general, in all the cases, we found that the field spectral data present better predictions than the laboratory spectral data. But one of the most important things is that the beta coefficients reveals that there are several spectral properties that we lose once the samples are collected to the laboratory. And the beta coefficient summarizes what we lose in general, not only one sample. For example, in the laboratory here, it's not really clear what the soil spectral properties the model is considering. And in general, it's possible to highlight just the carbonates absorption. On the other hand, here we can see that the model take advantage from hematite spectral properties, hygroscopic water, clay minerals, etc. Once we show the beta coefficients of the spectral based models that were created using the Kubert spectral resolution, the results are similar in the way that the spectral features that the models shows are not the same. Here we found similar conclusions when we use the sandy soils, and the same when we use the clayey soils. And because the study site of Alento was mainly represented by clayey soils, we used this model, which is the field-based model using the clay dataset to apply it in the UAV platform in order to predict the water infiltration rate. For the radiometric calibration, we calibrated the DN values to an add-on before the flight, and here you can see that the spectral response of the different targets with increasing albedo, it was very similar. So then I continued with this data, and here you can see the study site with the samples that we collected in field and the masked pixels in red. Also here in black, and greener values shows that the infiltration rate is higher, and redder values indicates a lower infiltration rate. Then I performed the interpolation with the measured water infiltration rate, and also with the predicted water infiltration rate in the 100 pixels that were randomly selected. Here we can see that the maps appears to be very similar. This is the validation in 5 samples that were not part of the calibration of the model that they were collected in Alento, and here we can see that there is a nice correlation. And to conclude, this study showed that the soil surface reflectance is a good tool to predict the water infiltration rate. The beta coefficients revealed that there are quantitative spectral properties of iron oxides and organic matter that can be lost once the samples are collected to the laboratory. In all the cases, the field spectral based models showed better results than the laboratory spectral based models. Even using with the whole data set, it is possible to generate a generic model, and the contribution of the shortwave infrared spectral range was considerable, because after the resampling process, the model showed a worse performance, and the results that the model that was applied to the UAV sensor were successfully validated in field. That is.
Thanks.
If we have more time, I can present other experiments that I performed using the thermal spectral range.
Okay, but before that, are there any questions? Maybe, yeah, Salvatore?
Yeah, maybe one. Okay, it's about the potential of this methodology. I see the effort in trying to test 2 different data sets and see their potential in order to predict water infiltration rate. Of course, from my perspective, the biggest potential rely on the use of spectral soil library. And my question is, consider the results that we have seen in this presentation, do you think there is any possibility to improve the quality of this data and the potential of its applicability, for instance, in removing noise eventually from drone data, or with a specific procedure? So what we miss in this?
I think that we don't miss so much with the drone data and with the field-based measurement. The loss here is with the laboratory measurement. And the idea here is to improve the performance of a lab-based datasets. Because
no, but in fact that's what I mean. That's what I meant. How can we improve the value of lab dataset, because the lab dataset can actually be used in a bigger dataset, and it can be used by any scientist in different parts of the world. Can be valuable for the others, no?
Yes, of course. Now we are also working in generating a correction factor to make the lab-based datasets more applicable to soil surface dependent properties. One of the problems is that every soil is different. So it can be a relevant correction factor for the specific dataset that I am working with. But then, in order to make it applicable to every place, this is the challenge.
So it's an open question.
It's an open question that we are working on it.
Okay.
Sure.
Thanks a lot. Then I think, thank you. Nicholas, can you help to stop sharing the screen? And then we move on with Brigitta.
Hi, can you see my screen?
I think not yet.
And now?
No, not yet.
Okay.
So if you say present now, select Windows, but you need to open the PowerPoint first.
Thank you.
Okay, now it's coming, yes.
It's okay.
Yes.
So I would like to talk about how we use machine learning in hydropod transfer research and how it can be useful for the UAV survey. First, just let's see fast what is pedotransfer function, what it means. This term was introduced by Bauma, and these
Brigitta,
functions help to translate soil data we have into the data we need.
Brigitta, the second
yes.
slide was not showed.
Do you see it now?
I only see the starting slide.
Okay, I don't know. I don't know why.
No.
Yeah, now we see it.
Second slide.
Is it okay now?
Yes,
what
I
can
can
you
see it.
Okay, so then for these pedotransfer functions, what can happen that we add more and more environmental covariates to make the predictions more robust, and these environmental covariates helps us when we would like to apply the predictions to prepare maps. And this is also an interesting connection with the drone research. So how those kind of covariates what we can get from the drones can support the mapping, for example, the soil hydraulic properties. And as we go towards this direction, there are several studies which are on this aspect of the transfer functions. They use hyperspectral data as input to get different kind of soil properties, and the term they use for this kind of study is spectrotransfer functions. And this was introduced by Lagacari from France, and then it was used also by Babayan, who worked with Ferrecan, who is a very well-known expert in soil physics, and they used the spectral data to estimate soil hydraulic properties. So it can be very interesting for us to go on with the research we are doing in iAqueduct. Can you see my third slide?
Not yet.
I don't know why it is so slow.
Okay.
Okay, so here I try to give a fast overview of the most recent pedotransfer functions which were derived to predict the soil hydraulic properties. You can see that it is more and more often that people are using machine learning methods. It's getting easier to use this kind of methods because statistical softwares are including these methods. In the beginning, when people started to use this kind of methods, they found that the biggest difficulty is to have enough capacity, computer capacity, to apply these methods when there is a big data set. But it is again better and better solved by the softwares because already parallel computation is included inside. So you do not need so much coding skills to be able to use these methods. From these methods, a lot of studies found that random forest is one of which is very good to apply. It has a good prediction capability. Further to it, you can calculate the uncertainty of the predictions as well, and it can handle any kind of input data. So you can have both categorical or continuous data as an input. It is also very important when you would like to work a lot of different kind of data or land cover with topographical indices and soil properties. So this is a good method, and further to it, it is not that complicated to use it. And another thing is that it can work with a lot of input variables. This is also very positive if we think on the drone research, that we have a lot of spectral bands. So being able to handle those lot of bands without losing information, random forest can be very helpful too. Yes, of course, people are using this PLSR method, but it would be nice to see what combination of methods would be the most efficient. And so let's go on. So what?
Brigitte,
yes?
Can you try to use mouse and then you click to the specific slide? Which slide now you are in?
And global and regional gridded soil hydraulic maps is the...
Yeah, but this slide is not moving, right? From my screen.
No. Sorry, so
No,
you don't see...
I saw your screen, but not the slide you are talking to.
I have no idea why it is
okay.
not going.
Did you use
And
mouse? You can use mouse to click to
I have
those
the mouse.
slides. I don't know. Oh.
Are you
Maybe
sharing
Yes,
the screen?
let's
or the presentation.
Presentation.
I shared it. Then
Oh
I
yeah,
go
now
out.
we see it. Now it's moving.
moving.
Yes.
It's good.
Okay.
Okay, so then I leave it.
Yeah,
I leave it
yeah.
like that.
Yeah,
right?
this is better. Yeah.
Okay. Okay, sorry. I don't know what the problem. Okay, so then let's move on. So if we have this kind of prediction transfer functions, then it is interesting how we can apply them for spatial data sets and to prepare gridded soil hydraulic maps. It was applied regionally, globally, and already locally. There are several studies. Here I just thought to show a few ones, maybe the global and one regional one. So just to show a possible way to go on to apply these transfer functions and what we could reach if we would have the capability to use the hyperspectral data and prepare transfer functions with the use of them. This is another example how soil hydraulic maps could be derived. So in this study, we were focusing on direct methods and indirect methods. We called the indirect methods where the path transfer functions are derived on a training data set. And then those transfer functions are applied on covariate layers, environmental covariate layers like topographical indices, information on vegetation, and available soil maps. Then we predict certain soil hydraulic properties with the PTFs. So then we get the soil hydraulic maps. And compared how the accuracy might change if we use a direct method. The direct method we code when we use geostatistical methods, and this is a more recent kind of method where when random forest is applied to understand the relationship between the environmental covariates and the desired soil property, here soil hydraulic properties, and then it was combined with the kriging. And when we were working with geostatisticians, we saw that, okay, it's kind of PTF with the kriging method, but for the PTF, the local, only local soil profile information is used. So it was very interesting to see how to combine these different methods and what will be the difference between these geostatistical based soil hydraulic maps and these indirect PTF based soil hydraulic maps. And what we have found that, first I would like to tell you what you see. So the first map is the soil hydraulic map prepared with the geostatistical method. Then the B map is which was prepared with the pedotransfer functions. These pedotransfer functions were derived for the full Hungarian soil hydrological data set. Here for the geostatistical methods, only those samples are used which are on the study sites. And then we checked as well how the European soil hydraulic maps look like and how accurate they are for the study site. And we found that both methods, which are based on the local data and locally derived methods, are significantly more accurate than the continental data. And it was, of course, expected because everything is local. And it was nice to see that if we have local data, we can get the more extreme values. This can be seen from the different colors because the color scale is the same for all the maps. And the difference between geostatistical method and the PTF-based method is not significant at all. So the performance were very similar. And this was an important result for us because here we wanted to see how far we can get if we have a more general pedotransfer function. And here what helped us that in these pedotransfer functions, we not only included the soil properties, so just sand, silt, clay content, organic matter content, pH, calcium carbonate, but we added also environmental covariates. So we could analyze 172 covariates. And these other two maps show the information about the uncertainty of the maps. So here I would like to show you the advantage of for example, the random forest, in which the uncertainty computation is included. You can get information about it, and then it's nice that you can map as well. And on the right side, we computed the difference between the lower 5% values and upper 95% value, so it means the possible lowest and possible highest values, and we could see that the uncertainty is higher, so where it is darker, where we have soils with high organic matter content, so kind of histosols. So it was nice to see the relationship that, okay, it was logical because we do not have as many histosols in our national soil hydraulical database. So of course, for which we do not have so many data, we might not be able to describe so well. And we have recently worked on the European pedotransfer functions because we could, the first version, when we published it, we focusing very much on the applicability of the PTFs. So we wanted to use those kind of methods which performs well but easy to use. But then in 5 years, the methods and the softwares developed so much that it was not anymore a barrier to use more complex models, and it was obvious that if we will use a kind of machine learning method, which is an ensemble type, which means that a lot of models are inside the one final model, of course it will be more robust and will perform much better, I mean significantly better than the previous one. So we decided that, okay, it's time to renew those PTFs. And another thing that was a driver to do this, that we thought it would be nice to show also the uncertainty of the predictions for the users, which can be interesting in different kind of modeling. So what we did that we derived the point predictions, which means that we predicted specific water contents. So we predicted saturated water content, the field capacity, the wilting point, the plant available water. So this is it's based on the field capacity and wilting point. And we predicted the saturated hydraulic conductivity and the Muller and Funkington model parameters to give information about the moisture retention and hydraulic conductivity curve. And here another plus compared to the version 1 EU PTFs is that we included, we analyzed much more input combinations in the PTFs. We decided that the minimum set should be the sensate clay content plus the soil depth. It's again something plus that here we did not just differentiate the topsoil and the subsoil, but we added the soil depths because we saw that the users know this, that how deep they would like to apply the pedotransfer function. And then what we included as optional input parameters and combination with the minimum set, it was organic carbon content, bulk density, pH in water, calcium carbonate content, and cation exchange capacity. And here I would like to give you a picture about how many samples could be considered for the new PTFs. Of course, it is very similar compared to the first version because we worked with the exact same data set. And here it can be interesting too that based on which combination is considered as input parameters, how the number of the samples change by the predicted soil hydraulic property. Of course, when all the input parameters are added, so both chemical and physical parameters, then the predictions are based on much less samples. So this we considered, but at the end we could show for which parameter combination which pedotransfer function is applied to use, because maybe for the theta saturated, even if you add pH and calcium carbonate, you do not get closer to the prediction because it is mainly, anyway, the most important, the bulk density. So if there is no more improvement adding further parameters, then we gave information, okay, then you just use the PTF7, which is based on much more samples, it is more robust, and so this is the way to go if someone would like to predict with these PTFs. Here I would like to give you some information about the performance of the new PTFs. These performances are comparable what is in the literature, so it is around 0.04 cubic centimeter per cubic centimeter. When there is information about the bulk density, the theta saturated can be predicted with much more smaller error, of course. It is interesting for the saturated hydraulic conductivity. We could not go lower than 1 order error, so it is log 10 centimeter per day. So if we check it is in centimeter per day, it is maybe a 1 order, and this is due to the different measurement methods which is in the EU HIDE dataset, which we used to train the PTFs. So there are a lot of different methods, and this is why this case set could not be predicted more accurately. If the methods are more harmonized in a database, then maybe you can go down to 0.4 log 10 centimeter per day. Okay, so let's go on. We compared if the point predictions or the parameter predictions are more accurate if we only need specific water contents, so the theta saturated, the field capacity at 100 centimeter metric potential or at 330 centimeter metric potential and wilting point. This is interesting for people who don't need the full retention curve, but only these points. So for them, it is better to use the point predictions. There are not much difference. Sometimes the point predictions were significantly more accurate. So the best is to use the point predictions. It's if not the full curve is needed. Then we compared the new PTF, we called it LPTF version 2 with the LPTF version 1, and we found that 14 out of 19 cases, the new PTFs, the version 2, performed significantly better. And in the rest of the cases, there was no significant difference. So it shows that using the random forest method, you really get more robust predictions. And we wanted to see how much we can get information about the interpretability of the model, because for machine learning, it is often told that, okay, when you would like to give information for practical use, you would not use machine learning because those are difficult to interpret. For the random forest method, it is not the case, because you can calculate the variable importance, which is very interesting information for the users. So which soil property has the biggest influence on a certain soil hydraulic property. And with the partial dependence plots, you can analyze the effect of a given or two given soil property on the soil hydraulic property. So it is nice to see. So here, for example, if you would like to predict the saturated water content, the bulk density is the most important. Here you don't have information on it, but we analyzed and we got it, and it's usually known. And you can see that if bulk density is low, the organic carbon content does not have any effect on the prediction. And if you have a denser soil, then okay, increasing organic carbon content can increase the saturated water content, but we can see that the bulk density defines this soil property. And for the other ones, it is even more interesting to see the combination, how those influence a given soil hydraulic property. And to make the use of these PTFs easier, we developed a web interface for these algorithms. It is a small picture, but here you can just upload your data in a CSV file. Then you can select which kind of soil hydraulic property you would like to predict. Then you can see what kind of soil properties are available for the predictions based on your dataset. It can help to check for the user if all soil hydraulic properties are included what he wanted to use. There is information about how the column names should be formatted for the program being able to recognize them. And here, based on the input parameters and what you would like to predict, it is automatically written which kind of PTF will be applied. And then you can select if you would like to get information about the uncertainty. So here there are predefined quantile options that you can select, but you can even customize by yourself if you would like to compute something different. Then you just have to push start calculations, and in the output box you can see the first 10 predictions to have a look at it if it is the one what you needed, and then you can download the results in a CSV file. The predictions were derived in R, so the R scripts which were used to build the models are available in a GitHub page. It is also archived in Zenodo. And here are the availability of materials which are connected to these new algorithms. And to move on to iAqueduct, so how these could be useful for the project, in which these transfer functions are important to derive soil hydraulic properties, and we are working on it in the second work package of the project. Here our aim is to compare the performance of available pedotransfer functions and also derive spectrotransfer functions, being able to predict the soil hydraulic properties of the top layer. And here we try to combine soil spectral libraries, but we are just at the beginning of this work with all the participants of the project. Then some conclusions that so the advantages of the machine learning methods, for example, the random forest, that it can handle mixed data type, has strong predictive power, can handle a lot of input parameters due to its randomization and ensemble kind of structure. Then uncertainties of the predicted soil hydraulic properties, if we focus on this soil property and model parameters, can be computed. Then it can describe non-linear relationship between predictors and response, which is important because these relationships are not linear, but even if those are linear, those can be described. Okay, then that way the linear regression is the simplest thing. So of course in this case you always have to consider which method makes sense to use. And the marginal effect of predictors on the response can be analyzed with the partial dependence plot. So the difficulty of the interpretation is much lower for the random forest method. And this partial dependence plot can be computed also for other kind of machine learning methods. Something other which can be interesting when we would like to use these transfer functions to map a soil property, that the resolution of the aimed soil property is determined by the resolution of the most important predictors, of course, but it is not not in this way all the time, but we have to consider always this. And another thing which needs to be kept in mind, that mapped uncertainty is not location specific, but depends on the input data, on your training data, what you use to derive the transfer functions, and your algorithm, what you used. So being able to interpret the full uncertainty, which is in your mapped solve property, you need also the uncertainty of the input layers. So if you use 50 environmental covariates, you need to have an information of that. So then it is quite complex. So thank you very much for your
Thanks a lot, Brigitte. It's very interesting. Maybe I have one brief question and then we move on. I saw for the hydraulic conductivity, you have VZ, van Noten, I guess. But the unit is cubic centimeter. Can you go back to that slide? Maybe I missed something there. Yeah, here. So you said the VZ moisture retention. What does it mean? And this is mean the curve, retention curve.
Okay, so the VG is the yes. Okay, so this is it is for the water retention. So this is the mean root mean squared error curve. For the full curve, and here we computed the error in the following way. So we predicted the van Noten parameters based on the input variables. Then with these predicted van Noten parameters, we computed the soil water retentions for those the head values, metric potentials, where we had measured the water retention value in the data set.
Okay.
So in this way, the water retention predicted with the predicted van Noten parameters are really compared to measured one.
Oh, that's a very unique data set. Yeah. Yeah.
Yes, it is.
Yes. And then the last one is about this case set, and you at the end you have some modern van Noten hydraulic conductivity. So the difference between the two, I'm not very clear.
Okay, yes, okay. So this, the Ks is the saturated water content, and so this is measured with the methods which are applicable to get the saturated hydraulic conductivity. And then this, the MVG hydraulic conductivity, this is what you have after fitting the Moellen van Noten function. So this is the hydraulic conductivity in the full suction range.
Okay.
And here we predict the parameters of the Moellen van Noten function. So the function and the Moellen. And then we here again compute the hydraulic conductivity, which is not saturated anymore because it is in the full suction range. So then we predict the hydraulic conductivity at each metric potential.
Okay. So it's unsaturated one, and you have the curve.
Unsaturated.
Okay. Thanks a lot. Are there any further questions? If not, we move on. Sorry, I think the time is really going off, but I think it's very interesting for lots of discussions. So, Luozhan, could you help to share your presentation?
Yeah, sure.
Yeah.
Yeah.
Hide the presenter if you. Okay.
Okay. Okay. Okay, my presentation will be like a short, and it's still research ongoing. So maybe I need more like a suggestion from your side, and I can improve my results. Okay, the study area is still the Montefort Cilento, which we did like 2 field work there, once in 2018 and one in 2019 in June. The methodology is it's like downscaling based on random forest. Use like 1 kilometer resolution data to train the model and generate the random forest model to predict the US-based resolution data. The features I used include the land surface temperature. I used 5 years data, and the NDVI data also 5 years. The land surface temperature difference, which calculated from the land surface temperature from daytime and nighttime, and also the daily average of land surface temperature. Others, the apparent thermal inertia, it's calculated based on the land surface temperature difference and albedo. Also, the DEM, slope, insolation, and the topographic index, also the porosity. Here we tried like all the combinations, exclude the situation without any land surface temperature data. And try to find out how do they work at both large and small scale. Here is here's the fine resolution UAS data. We did the field survey with a graded flight. We obtained the RGB and the multispectral and the thermal data from June. And from this data, we got the NDVI, also albedo, and the land surface temperature, also the features generated from land surface temperature. Here is like a description of both the coarse and the fine resolution data. First, for the coarse resolution, we used 1 kilometer resolution satellite data with 30 multiplied 30 kilometers. The land surface temperature, albedo, and NDVI are all from the MODIS. The land surface temperature daytime is from like 1:30 p.m. Also, like the nighttime is from 1:30 a.m. Which compared with US data, it's like from 1:30 p.m. and like from 5:30 a.m. We calculated both of them, like the land surface temperature difference and average. Also, like for albedo, for the apparent thermal inertia, we calculated from the satellite land surface temperature and albedo. Here we generate the albedo from the UAS multispectral data and the thermal data. And the NDVI is also from MODIS and US. The LST, albedo, and NDVI, they are dynamic features. We use like 5 years continuous time series. The others are the static features. We use the same map for these 5 years. The porosity are from the soil grade, bulk density, and DTM are aggregated from a 5-meter local data DTM, And from the DTM, we calculate the slope aspect and then the topographic index and the insolation. The same with what we did for the fine resolution data. From DTM to slope and the others, but here we just do interpolation based resampling from this 5 meters local data to 6 centimeter resolution DTM data. Then here is the in situ soil moisture data. In Alento site, with the help of Professor Nunzio's group, we have like a soil net soil moisture, which is like a continuously several years measurement of soil moisture, but it's at 15 centimeter depth. And here we have the TDR data, which measured on exact that 2 days of field survey. Actually, they have a bit like a difference, like we can find in the results. Here, I try to like found the season separation of like this sets. If we plot the in situ soil moisture data, we can find like the separation of wet season and dry season. So the 2 survey for us are both located in the dry season for me, like October and June. So I try to like train the model with like a seasonal separation of the important features. Here we have some results examples. Like for this example, we use the features of land surface temperature average and land surface temperature difference, NDVI, slope, topographic index, and DM, which land surface temperature has the highest importance. Yeah. If we go to the validation results for 2018 October, use the SoilNet data, we can see like a relatively good results in terms of RMSE. We had like 0.03, but we can see we only have like 9 points for validation. Then if we go to like 2019, because we have a relatively larger survey area, so now we have like 14 data for validation. The results, like if it turns to like MSE and R, it looks all right, but seems the pattern of the predicted soil moisture is kind of smooth. Here, like yeah, it's just a kind of smooth, and to extend the validation data number, we try to like validate both 2 surveys together, like to extend the validation number to 23 points. Then the results is like IMSE with 0.05 centimeter, like the volumetric soil moisture, and with an R of like 0.56. The other thing is, if we compared with the results of like SoilNet and the TDR data, they are completely different. Like from my side, I found maybe the SoilNet gives a better results compared with TDR. But the SoilNet data is from like 15 centimeters. The TDR data should be like in a shallow layer. So this leaves like a question, which one should I use? And here we have another example. The only difference with the previous one is if we included the land surface temperature difference. And like in this case, we can see if we compare with the test results and the validation results, the validation results is even better than the testing results, which the testing results is at a large scale, and the validation results is at a small scale. Maybe like it means some features can work better in small scale. In the other hand, like some features works better in a large scale. And here we can see like the porosity has a high importance, but actually for the validation set, for the field set, we only have like 20 points porosity data. Although the validation results at this 20 these points data showed good results, but if we want to generate a soil moisture map, use this data, the interpolated porosity can cause some uneven of this soil moisture map results. Here we have some simple conclusions. Some features may matter in small scale and large scale are different. For example, the topographic index slope also the porosity may influence more in small scales. And surface soil moisture in dry and wet season can have different relationship with other features. And maybe more efforts are needed in this research.
Thanks a lot, Luda. It's already updated very much from the last discussion.
Yeah.
Can I ask a question in terms of the small scale? What do you mean? Yeah. Slide number 9, I think. Yeah, slide
this
number
one?
9, yes.
Yeah.
Small scale,
mean, I mean the small scale means in Monteforte Cilento, in the MFC sets, 200 meters multiply 150
Oh, okay. So you
meters.
trained only utilizing that small pixel, you mean?
Oh no! It's I mean the validation results is even better than the test results.
Yes, and this testing result is utilizing what data?
Sentinel data, a 30 kilometer multi-30 kilometer with 1 kilometer resolution.
Mm-hmm. But then this is also the same as the previous one. So I didn't get it still.
Yeah, right.
So these two, you are utilizing the same data training, but then this one you don't call it the small scale.
No, it's also a small scale. The difference is here we have also a good results for the testing, like the IMSE and R. And compared with for example the validation data, they show similar results. The testing, testing is at a large scale, and here the validation is at a small scale. It's just a comparison between a large scale and a small scale.
And what leads to the bad testing result then? So what's the major difference? The next one, the next slide.
The next slide is here we can find a poor testing results actually.
And what's the reason for this poorer testing result?
The only difference between these two tests is if we include the land surface temperature difference. Here is just an example, just some. The only difference is the land surface difference, because here is only land surface temperature average, porosity, insolation, DM slope, and here we have both like land surface temperature difference because it has a high
It's
importance.
very interesting. I mean, the things that validation result can be better than testing result.
Yeah. So like we have a lot to explore from all these results because I tried more than 400 combinations. They show like a different performance.
Okay, thanks. Are there any other questions?
Maybe just
hey,
a quick
Paulo,
comment,
please.
if I can. Hi. Maybe we need more points, more measurements for validation. So maybe next time we can organize a more extensive sampling with the TDR, and also by associating some thermogravimetric method, because there is a lot of uncertainty also in the measurement itself. So don't take the measurement as reliable and real and true. So we need to next time to improve the sampling campaign by increasing the number of points, the number of positions, and the coupling to the TDR, some thermogravimetric method to check up if the TDR has a large error. So,
Indeed, I mean, I fully agree with what Paulo suggested. For the time being, we only have 2 flights, and they are separated in 2018 and 2019. Maybe we should organize a campaign a little bit longer, and then you have the flight continuously, for example, every day or every to make it time independent, let's say, like what Salvatore also mentioned previously.
We will, Paolo, as I said to Nunzio, if I can provide just a quick comment. I totally agree about the need to increase the number of measurements at the ground, but also the number of flights. In this, I'm available in the next week, starting from next week, for a flight. So if we can identify together, the Italian group at least, a campaign just to integrate a few points, this will be good.
Yeah, indeed.
Yes, I agree, and also I suggest it would be ideal if we can organize a campaign during the dry season, but also in the wet season if it's possible. To see the difference between, because we got 2 days during the dry season.
Yes.
It would be interesting this time to organize an extensive campaign in the dry season and another one in the wet season. And we are available from next week on, so the owner cut the grass, I think, so the land is it should be practical to walk around the field and collect samples, because the grass was very, very tall and dense. But it should be okay next week, so we should be ready to organize the field campaign during the flight.
So if if you think about the possible dates, we can organize something. Probably it's better if we talk later after the end of the meeting.
Thanks a lot.
Okay.
I guess, wow, the meeting actually much longer than expect. It's 1 hour more. But I guess this happens. It's very interesting discussions. So later on, I will try to make the video available through YouTube, and Salvatore will help to upload it to website. There are definitely following up to have more discussions, but then we can start it from here to figure out some more details in terms of the working group, but also in terms of other relevant science research and other projects, right? Okay, so with that, thank you all for taking your time and stay this long. Let's hope we can meet physically face-to-face in a very near future.
Yeah, I can only, before we close, I would like only to say, it would be nice if we plan something more focused on the work of the guidelines in the near future. So this might be the aim for the next meeting. And in this direction, I can inform you all that the book has been accepted by Springer. So somehow some of the outcomes of these activities can be incorporated in a book chapter published with Springer that can be an excellent outcome for the project Harmonious, but also for Water JPI. So I help with it. So we have this good announcement, and this will put in a frame of deadlines shortly some of the deliverables that we are willing to
that's very good news. Great to know. And maybe later on, Anna and me and some of other colleagues, we can gather together in terms of the guidelines, how to make a structure out of it, and based on today's discussion, how to go from here, for example. Yeah. Okay. Yes, good. Then I guess it's time for a lunch break. Okay. Thanks a lot.
Sure.
See you. Ciao. Bye.
Ciao.
Bye. Bye.
Bye. Bye. Bye.
Bye bye.
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 Bye.